In this video, we're going to talk about the fundamental theorem of calculus. So before we do that, let's just remind ourselves about how we think about the definite integral from a to b of f of x. So the first way we talked about this is as the limit as the number of rectangles goes to infinity of the sum of the areas of these rectangles. So the sum from k equals 1 of delta x times f of xk, where xk is any x value within the kth interval. Maybe I should write that. So it's an x value in the kth interval. Okay, so this is the area. Maybe I'll put it in quotations because it could be negative. So the area of the kth rectangle. Okay, so then we also think of this as signed area between y equals f of x, the x-axis, the vertical line x equals a, and the vertical line x equals b. Okay, so signed area, because if f of x is negative, then those rectangle areas are going to be negative. So we would want to count that negative part as a positive area, but here it counts it as a negative area. So maybe I'll just write it's the actual area if f of x is non-negative, so bigger than or equal to 0, on the entire interval, so on a to b. Then we get the exact area, the actual area. But if we allow f of x to be positive or negative in the interval, then we call it signed area. Okay, in the last video we saw also that it is the total change of capital F of x, okay, where capital F of x is an antiderivative of little f of x. Okay, so the derivative of capital F of x is little f of x. Okay, the total change of that function on the interval from a to b. Okay, so here little f of x is the rate of change of capital F of x. Okay, so that's another way to say that capital F of x is antiderivative. Okay, now we also, because of this last one, we know how to, if we knew capital F of x, we know how to find total change over the interval. Okay, the total change over the interval is going to be f of b minus f of a. Okay, and this is actually the fundamental theorem of calculus, so this idea. So if little f is a continuous function on the closed interval from a to b, and capital F of x is any antiderivative, okay, it doesn't matter which one you use, then the definite integral of f of x dx from a to b is going to be the antiderivative evaluated at b minus the antiderivative evaluated at a. Okay, so this is the statement of the fundamental theorem of calculus. Okay, now this is actually a very important theorem because when we started talking about the definite integral, okay, we started talking about areas of rectangles. And you might have been, or you should have been maybe, quite unhappy that the notation is so, and even the name is so similar to the indefinite integral, because they seem very different, right? If this is the area of a bunch of rectangles, the indefinite integral is just the antiderivative. It's a family of all antiderivatives. So this is actually what brings those together. Okay, so we find an antiderivative, and then the definite integral is the antiderivative evaluated at two different values, so the endpoints of our definite integral. Okay, so now because of this, we want to use some special notation. This is just to have sort of, it's so you can write everything in line where it makes sense. So you can give the antiderivative that you're using before you actually start plugging stuff in. Okay, so what we normally do, if we wanted determine the definite integral from a to b of f of x dx, we would first find an antiderivative. Okay, so f of x. We don't need the plus c because we get to pick our favorite antiderivative. And then we would use the notation with a vertical line and write a, b on the top and the bottom like that. So what this means is it's capital F of x evaluated from the lower limit to b, the upper limit. Okay, and then in the next line you can do f of b minus f of a. Okay, so it's a way to give this intermediate step so that I know and you know when you're looking back what antiderivative you actually used. Okay, so this is going to be before you plug in your x values. So note, the fundamental theorem does not require that my function is non-negative on the interval. Okay, so what that means is that they're not saying that the definite integral, when you compute this, you might not get the area, okay, under f of x. Okay, remember, this is equal to the signed area. So it might not be the area, and in fact, it could be a negative number. Okay, so don't let that confuse you. It's related to the area, but remember it's the signed area. So when we compute it using the fundamental theorem, you might get a negative number. Okay, so if the question is asking for the area, then you need to be more careful. Okay, so we're going to do an example of that. One other thing that I wanted to note also, so when you compute the definite integral from a to b, f of x dx, okay, you're going to get a single number. Okay, so that's the definite integral. When you compute the indefinite integral, you get an infinite family of antiderivatives. Okay, so don't let these, don't confuse these, okay? They're very different. This is just a number. So even though the notation looks very similar, these things are very different from each other. Okay, so in this one you get just a number. In the definite integral, you just get a number for your answer. Here I get an infinite family of functions. Okay, so they're very different. So at this point, now we are able to figure out how much medicine that patient actually got in the question in the last video. So remember that f of x is x squared plus 20. This is the rate. Okay, so earlier we showed that the amount that the patient got was between 25.72 milliliters and 26.97 milliliters. Okay, so now we want to compare using this idea. So what I'm going to do is I want to find an antiderivative. So I want to find capital F of x to be an antiderivative of my little f of x. So I want the antiderivative of x squared plus 20. So I can do this separately. So using the power rule, the first part is going to be 1/3 x cubed, and then the 20 is going to be 20 times x. And then I have my constant plus c. So that's my antiderivative. I'm just going to use this part. Okay, so what we're actually looking for, so the amount of medicine in this between the second and third hours is going to be the definite integral from 2 to 3 of, I'm not going to write f of x, okay, so from my function. So I'm going to use my antiderivative 1/3 x cubed plus 20x, and I'm going to evaluate that from 2 to 3. So that's going to be this whole thing evaluated at 3, so 1/3 3 cubed plus 20 times 3 minus the whole thing at 2. So that's 1/3 2 cubed plus 20 times 2. Okay, so this is f of 3, and this is f of 2. Okay, so if we compute that, we should get 26.33 milliliters. Okay, and notice that this amount is, in fact, between these two amounts. So we were right in the fact that we had an underestimate here and an overestimate here, and our amount was right in the middle. Okay, so that now that we have the fundamental theorem, we're able to compute this without determining the limit of that sum, which is not fun to do. So let's try and do a couple more, just to get the hang of this. So for here, I want to find an antiderivative of 4t cubed, where t is my variable. So I know that t to the 4 has derivative 4t cubed. So now I want to evaluate this from 1 to 2. So I'm going to plug in 2. So I have 2 to the 4 minus when I plug in 1 to the 4. So that's going to be 16 minus 1, so 15 would be my answer there. Okay, now one more. So now I want an antiderivative of 1 over x. So remember, this 1 over x is actually x to the minus 1. And minus 1 is the only exponent that we cannot use the power rule, the reverse power rule for. So we want to remember what has derivative 1 over x. Okay, and we know that that's ln absolute value x. And I want to evaluate that from 1 to 5. Okay, the absolute values doesn't actually matter here because we're putting in positive numbers. Okay, so that's going to be ln of 5 minus ln of 1. Ln of 1 is 0, so this is just ln of 5, which is approximately 1.609. Okay, so that would be our antiderivative, or our definite integral, sorry. So some properties for definite integrals. So some of them are the same as for indefinite integrals, so similar. So 2 and 3 in particular. Let's just start with 2 and 3 actually. So here I have a constant times the function. So just like we can with indefinite integrals, we can pull out the constant and do the definite integral on its own and multiply the constant after. Okay, so that's when k is a constant. Okay, if we have a sum or difference, we can do those things so separately. So I can go from a to b of f of x dx and then add or subtract the definite integral from a to b of g of x dx. Okay, so either way, whatever you want to do. So now 1, 4, and 5 are sort of new. Okay, these are different than what we had with indefinite integrals. So here, notice that the upper limit is equal to the lower limit. Okay, in this one. So it goes from A to A. Okay, this one is actually going to be 0, always. So if you think about the fundamental theorem, it would say that if we had an antiderivative, I'm going to do f of a minus f of a. Clearly that's going to give me 0. But we can also think about this in terms of area. Okay, so if this is my function, okay, it doesn't even have to be positive, but I drew it positive. Okay, and here's a. We're going from a to a. So the area that we want is just a vertical line. Okay, so this has no width. So the area of our rectangle is 0. Okay, so the width is 0. That there is some height, but there's no width. So we also get area 0. Okay, 4 and 5 are not very helpful because they're just definite integrals. So they're just different ways that we can compute them. So the first one, so if I had, I'm going to sort of describe it using an area. Okay, but it works even if the function goes negative. Okay, so here's f of x. And maybe I want to go from a to b. What I can do instead is stop at c. So take a little break at c. So I could compute the area under from A to C, and then add to it the area from C to B. And that's going to give me the area from A to B. Okay, so this definite integral from A to B of f of x dx, what we could do is go from A to C and then add from C to B. Okay, so sometimes this is useful. Okay, this is where C is between A and B. Okay, so obviously you want to stop somewhere in the middle. But you can do that. Okay, so this one would be the yellow area, and this one in the picture would be the green area. So if you add those together, you get the full area under the curve from A to B. Another thing that comes in handy sometimes, but probably not very much in our class, but in higher level classes, is sometimes it's more convenient to do the bounds in the opposite order. Okay, so I could switch the upper and lower bounds on the definite integral, but I need to add a minus sign. Okay, so if you think about this one, if we use the fundamental theorem, is f of b minus f of a. Okay, now if I think of this one, it's going to be minus f of a minus f of b because of the negative. If I bring the negative through, I get negative f of a plus f of b, and that's the same. Okay, so that's sort of an algebraic way to show why this happens. Okay, so let's do an example. So we can use the substitution method with definite integrals as well, but I'm going to show you two different methods. So the first one is where we change the limits. This is the method I prefer. So we're going to use our substitution. So let's let u equal 25 minus x squared. So then du is the derivative of this, negative 2x times dx. Now I don't have negative 2x, I only have x dx, so I'm going to move the negative 2 to the other side. Okay, so x dx is negative 1/2 du. But I'm also going to change the limits. So when x is 0, u is going to be 25 minus 0 squared, so 25. Okay, and when x is 5, u is going to be 25 minus 5 squared, so 0. 25 minus 25. So then, the definite integral from 0 to 5, I'm going to switch this. So it's square root 25 minus x squared times x dx is going to become the integral, so the 0 bound turns into a bound of 25. Okay, and the 5 bound actually turns into a bound of 0. Okay, these are the u bounds. Okay, so the top ones are for x, the bottom ones are for u. And then the square root is going to become a u, square root of u, and then x dx is negative 1/2 du. And now I can compute the limit. Just going to like that. So it is going to be, I can bring the negative 1/2 out. It's going to be u to the 1/2 du. So that's negative 1/2. U to the 1/2 is going to come from a 3 over 2, so I need to multiply it by 2/3. And here's why I like this method better. I don't have to switch back to x because these bounds are for u. Okay, so they're already in u. But we can cancel these 2's. Okay, so then I get negative 1/3 0 to the 3/2 minus negative 1/3 25 to the 3/2. So the first part is 0, and then this is going to be a plus, and it's 1/3 times 5 to the 3. So that's 125. Okay, so I get 125 over 3 as my definite integral. Okay, the other method you can do is to determine the indefinite integral. So forget about the bounds entirely. Oops, integral. Forget about the bounds entirely. So we're just thinking about the indefinite integral. I'm just going to rewrite it as 25 minus x squared to the 1/2 x dx. So I'm going to use the same substitution, which has the same du. Okay, and I again have to solve, or I'm going to solve for x dx. So negative 1/2 du is x dx. Okay, so then this is going to become u to the 1/2 times negative 1/2 du. So I can pull out the negative 1/2, and it's u to the 1/2 du. So it's going to be negative 1/2, and then it's u to the 3/2 times 2/3 plus c. So we get negative 1/3 u to the 3/2. Now I'm going to replace what u is. So this is 25 minus x squared to the 3/2 plus c. So that's my antiderivative. So the definite integral from 0 to 5 of our function is going to be the antiderivative, so negative 1/3 25 minus x squared to the 3/2, evaluated from 0 to 5. So now I put in 5 everywhere. 5 squared to the 3/2, and then I subtract, putting in 0 everywhere. And now so this is why I don't like this one, because now I have some work to do in here. These are things these are u values, essentially. So I'm going to have minus 1/3 0 to the 3/2 plus 1/3 25 to the 3/2. And again, I'm going to get 125/3. Okay, so what I don't want you to do is keep the bounds all the way through as x bounds, even when there's u's there, and then plug them in. Okay, that's not good notation. So you want to use either one of these methods. I prefer changing the limits because it saves you some work at the end. Okay, sometimes these antiderivatives are very complicated, so doing lots of work in here can get confusing. Okay, I want to do one more example here. We're talking about area. So suppose we want the area between the graph here and the x-axis, and the x equals -1, y equals 4. So I'm going to draw this graph, but you don't actually have to. Okay, but this one is sort of easy to draw. So it's in slope-intercept form. So it goes through the point at 1, and then it has a slope of -1/2. So this is going to be at 2, and then down 1/2. This is going to be at 4, -1. So I see I have this line like that. Okay, and then the area I want is from -1 to 4. Okay, so we can see that I'm going to have some positive area, but also some negative area. Okay, so I need to be careful here. And it switches at 2. Now, if you don't want to graph it, what you'd have to do is find, so without the graph, we'd have to find where in the interval from -1 to 4, y is, or f of x, is positive or negative. Okay, so you'd solve where it's 0, so -1/2 x plus 1 equals 0. We'd solve this, so that's going to be when x is 2. And then you'd want to check on either side, okay, of 2. So this is in our interval, so we think it's going to split there, so you'd want to check a point that's less than 2 and bigger than 2, just like we do for increasing, decreasing, etc., etc. So the area here is going to be, we're going to have to do it in two pieces. So I'm going to go from -1 to 2, and it's going to be the function, okay, the regular function. But then I want to add the interval from 2 to 4, again, of our function. Okay, but this one is going to be negative because it's under. So what I'm going to do is take the absolute value of it. So I'm going to get a negative number, and I'm just going to make it positive. Okay, so that's going to be, so if I take the antiderivative, it's going to be -1/4 x squared plus x. Okay, and we're evaluating from -1 to 2. And then I'm going to have the absolute value of the same thing, evaluated from 2 to 4. Okay, so if I plug in 2, and then I subtract when I plug in -1. Okay, so that's the first part. And then I want to take the absolute value of the second part, so plug in 4. Oops. And then subtract when I plug in 2. Okay, and then I need the absolute value. So when we compute this, I think the first part here, okay, so all of this, I think, simplifies to 9/4. And then in the absolute value, I actually get area of -1. So when I make that positive, it's going to be 9/4 plus 1, which is going to be 13/4, or 3.25 as my area. Okay, so the idea when you're finding area, you want to either sketch a graph quickly of y equals f of x, okay, or find the x-intercepts in the interval from a to b, and check x values around them to see if f of x is bigger than 0 or if f of x is less than 0. Okay, so that's going to split these into subintervals, or you could actually just absolute value each of these subintervals. Okay, you just might end up getting doing more work. Okay, so maybe I'll just write here the x-intercepts split the interval from a to b into subintervals. Okay, in these subintervals, f of x is either entirely positive or entirely negative. Okay, so you could, in each subinterval, determine if f of x is positive or f of x is negative. Okay, so f of x positive means the definite integral in that part will be positive, and f of x less than 0 means the definite integral will be less than 0. Okay, so the total area should always be a positive number, okay, and it will be equal to the sum of the absolute values. So you could just absolute value each subinterval, okay, of the definite integrals for each sub-region or interval. Okay, so you just want to break it up and do each part separately, and then if it's negative, make it positive. Okay, so that's the idea.